Hello, welcome to another module in this massive open online course. So, we are looking at the Fourier analysis of discrete time signals. We have completed our discussion of the discrete time Fourier transform, and in this module we will start a different concept, that is the discrete Fourier transform. Okay. So, we want to start looking at the discrete Fourier transform. So, this is the Fourier analysis of discrete time signals, and in particular of a very important transform for discrete signals is the discrete Fourier transform, which has revolutionized digital signal processing, because there is a very fast way to implement the discrete Fourier transform, that is the DFT, through the FFT, that is the fast Fourier transform routine. Okay, and that has resulted in a revolution in signal processing. Okay, so, it is one of the most important kind of transforms, especially since much of the processing happens in the digital domain. So, it is discrete time signals which are being processed by the aid of the DFT. Okay. So, this is used for finite length sequences. As I said, it is a very key transform. It is used heavily in images, audio and video processing, and for that matter also for communication applications, especially wireless communications applications and so on. So, it is used for finite length sequences, as I have already said, correct, and the definition is xn, consider a sequence xn, and this is a finite length sequence, 0 less than equal to, defined only for 0 less than equal to n less than or equal to n minus 1, and xk, the DFT coefficient, the kth DFT coefficient is defined as summation n equal to 0 to n minus 1 xn e raised to minus j 2 pi k n over n, that is the expression for the DFT coefficient xk, and this is defined for, this is also a finite length sequence, this is defined as for 0 less than or equal to k less than or equal to n minus 1. So, the limits of k are 0 less than or equal to k less than or equal to n minus 1. Okay. And this can also be written as follows, this can also be written as xk equals summation n equal to 0 to n minus 1 xn e raised to minus j 2 pi over n raised to the power of k n. Now, if I call this, denote this as W n, then I can write this in a very succinct fashion as n equal to 0 to n minus 1, and this now I can replace by W n to the power k n. Okay, where W n, note that W n equals, this is a fundamental quantity e raised to minus j 2 pi n, and also note that W n to the power of any integer k, or any integer, that is any, let us say L times n, equals e to the power of minus j 2 pi over n into ln e raised to minus j 2 pi L, which is equal to 1. Okay. So, this is in fact one of the roots of unity, that is what you can see. Okay. So, W n is e raised to minus j 2 pi over n, and the DFT coefficient xk is summation n equal to 0 to n minus 1 xn W n raised to the power k n. Okay, so that gives an expression for the DFT coefficient xk. Okay. Now, for the IDFT, note that for IDFT, note if you perform summation k equal to 0 to n minus 1 x k e raised to j 2 pi k m over n, that is equal to, now substituting the expression for x k, that is equal to summation k equal to 0 to n minus 1 summation n equal to 0 to n minus 1 x n e raised to minus j 2 pi k n over n times e raised to j 2 pi k m over n, and now interchanging the order of summation. Okay, so interchanging the order of summation, we will have this will be summation n equal to 0 to n minus 1, x n depends on only on n, so that comes out summation k equal to 0 to n minus 1 e raised to j 2 pi k over n into m minus n. Now, you can see this is equal to 0, this is basically the sum of the roots of unity is equal to 0 if m is not equal to n, and this is equal to, this is in fact equal to n if m equal to n. Okay. And therefore, this is equal to only the term n corresponding to m survives. So, this is equal to n x m. So, we have from this manipulation what we have seen is basically that n x m equals summation k equal to 0 to n minus 1 x k e raised to j 2 pi k m divided by m, which implies that x m equals 1 over n summation k equal to 0 n minus 1 x k e raised to j 2 pi k m over n, and in fact e raised to j 2 pi over n is w n raised to minus 1. So, this implies basically you have x m equals summation equals 1 over n summation k equal to 0 to n minus 1 x k w n to the raised to minus k m. Okay. So, this is the expression for the IDFT, inverse discrete Fourier transform. This is your inverse this is the expression for your inverse discrete Fourier transform. Okay. And this is of course represented by, similar to what we have seen many times before, you have x n equals x n and x k form a DFT pair, x n in the range 0 to capital N minus 1, k also in the range 0 to capital N minus 1. Okay. So, these form a DFT pair. So, both have n samples. Okay. So, observe that both have both the original samples and the DFT coefficients are n in number. Okay. All right. Now, the next thing we want to look at is we want to look at the relations between these various transforms, correct. So, we have seen several transforms, we are now seeing the DFT, earlier we have seen the Fourier series as well as the discrete time Fourier transform. So, we want to start by looking at the relation between this DFT and the discrete time Fourier series that is defined for a periodic signal, okay, periodic discrete time signal. Okay. So, what we want to look at is basically relation we want to look at the relation between DFT and DFS. Okay. So, consider the periodic extension of Xn consider the periodic extension of Xn, and then we have Ck equals 1 over n summation n equal to 0 to n minus 1 Xn e raised to minus j omega naught Kn. Okay. So, remember Ck, this is the, so we are considering a periodic extension of the signal Xn, okay, which is defined for 0 less than n less than equal to capital N minus 1. So, we are extending it periodically, which means we are repeating the same sequence Xn periodically, alright. So, it becomes a periodic sequence, and then one can consider the DFS of this periodic extension of Xn, and let Ck denote its DFS coefficient. Then you can see this implies that Nck equals, you can readily see that Nck equals n equals 0 to n minus 1 Xn e raised to minus j omega naught Kn. In fact, we have omega naught equals 2 pi by n. So, this becomes summation n equal to 0 to n minus 1 Xn e raised to minus j 2 pi Kn over n, which you can see is nothing but basically the DFT coefficient x of k. So, this implies basically that the DFS coefficient, so if Ck denotes the coefficient, the kth discrete Fourier series coefficient of the periodic extension, then n times Ck equals xk. Okay. And note once again that this is the kth, DFS coefficient of the periodic extension, and this is the kth DFT coefficient of the original signal. The original time limited signal, okay, with capital N samples. Okay. And the other thing that you can see is the relation between the DFT and the DTFT, that is the relation between the discrete Fourier transform and the discrete time Fourier transform, and that is also fairly simple. So, the next thing that we want to see is the relation between the DFT and DTFT. Okay. And now consider xn equals, now you form a signal such that xn equal to that is consider xn for 0, consider a signal xn which is 0 less than equal to for xn for 0 less than equal to n less than equal to n minus 1 and 0 otherwise. Okay. And for this signal, if you look at the DTFT, now the DTFT will naturally be x of omega equals sum of, because this is 0 outside n equal to 0 to n minus 1. So, this will be n equal to 0 to n minus 1 xn e raised to minus j omega n. Now, if you substitute omega equal to 2 pi k over n, this will become summation n equal to 0 to n minus 1 xn e raised to minus j 2 pi k n over n, okay, and which is nothing but xk. Now, you can see this is nothing but the DFT coefficient xk. So, this implies that your xk, this implies something very interesting, that your xk is nothing but the DTFT of x omega evaluated at omega equals 2 pi k over . Okay. All right. So, that is basically, that basically summarizes the DFT definition, the DFT, its relation to the discrete Fourier series as well as the DTFT, the discrete time Fourier transform. Let us now look at some properties of the DFT. So, we want to look at the properties of the DFT. Now, we have xn 0 less than or equal to n less minus 1 and xk 0 less than or equal to k less than or equal to n minus 1. N comma k are restricted. Now, of course, when we consider x n minus n naught, now it might go outside the range of 0 or n minus 1. So, what one can do is all such things can be restricted to modulo n in this scenario. Okay. So, what we mean when we say x n minus n naught in this case is that the n minus n naught has to be interpreted modulo n, all right, where n is the total number of samples. For instance, let us say we have n equal to 1 and capital N equal to 4. So, we have x tilde of 1 equals, let us say we call this as x of n minus n naught as x tilde. Okay. So, we have x tilde of 1 is x of 1 minus 4, I am sorry, n equals 5, let us say n equals, or n naught equals 5, n equals 4, n naught equals 5, okay, which is x of n minus 1 minus 5 equals x of minus 4, this is x of minus 4 modulo 4, which is equal to 0. Okay. So, this is basically your x of 0. So, x of x tilde of 1 where x is shifted by n naught equals 5. So, x tilde 1, that is the first sample of the shifted signal, is actually 0. So, basically you are sort of circularly shifting this, all right. The shifting is basically modulo 4, where n is equal to 4 is the total length of the sequence. Okay. All right. And now we look at the properties of the DTFT. And the properties of the DTFT are as follows. Again, the standard property, we start with linearity, which is simple yet fairly powerful and useful property. So, linearity tells us that if x1n has the DFT coefficients x1k and x2n have the DFT coefficients x2k and both have the same length, obviously 0 less than equal to n less than equal to capital N minus 1, then A1 x1n plus A2 x2n has the DTFT A1 x1k plus A2 x2k. Alright, so this is the linearity which we have seen many times before. Now, what about time shifting? Xn has the DTFT x of k. What can we say about x of n minus n naught? What can we say about this quantity x of n minus n naught? Now, let n minus n naught mod n equals m, all right. So, what we have is, so let n minus, so we have basically, let us denote this by x tilde or let us denote this by x tilde n. So, x tilde k summation n equal to 0 to n minus 1 x tilde n e raised to minus j, or basically we can just write it in terms of w n to the power k n. Now, let n naught minus n or n minus n naught mod n equals m. This implies n equals n plus, so with this implies n naught minus n naught is basically or n minus n naught is basically some constant L times n plus m. Okay. So, this is some multiple of this is some n minus n naught is some multiple of n plus m. Okay. So, which implies n equals n naught plus ln plus m. So, we have x tilde k, again x tilde k. Now, if you write x tilde k, x tilde k, this will be summation n equal to 0 to n minus 1 x tilde n, or basically x of n minus n naught, x of n minus n naught, remember x of n minus n naught w n to the power of k n. Now, remember x of n minus n naught has to be interpreted as n minus n naught modulo n, which is m. So, this will be summation, again m also goes from 0 to n minus 1 x of m w n to the power n raised to the power of k, and n is n naught plus ln plus m, and this is equal to summation m equal to 0 to n minus 1 x m w n to the power of k n naught into w n to the power of KL n, which is 1 into W n to the power of Km. Okay. And now W n to the power of K n naught comes outside because it does not depend on m. So, that is W n to the power of K n naught summation m equal to 0 to n minus 1 x m W n to the power of K m, which is basically this quantity is basically x k. So, this is W n times W n times K n naught into x k, which is similar to basically the modulation property, okay, or basically the time shift in time leads to modulation in the frequency domain. Okay. Time shift leads to modulation in the frequency. So, that is basically W n. So, what you have is basically x of n minus n naught has the DFT, which is W n to the power of K n naught, which is x k. Okay. All right. So, that basically covers the time shift property. All right. So, in this module we have introduced the DFT, looked at its definitions, some of its properties. So, we will stop here and continue in the subsequent modules. Thank you very much.